All right, let's do a couple more here. So we want to find the area of this parabola in this absolute value function. So we know this is a parabola, right? It's a quadratic parabola. And things that we know about the parabola, because, oops, this is negative, I know this parabola is going to go down like that. Make sense? Okay. Over here, I have an absolute value function. And I know the graph of my absolute value, especially because it's positive up front, is going to look like a V. Now, here's the other deal whenever I'm looking at my absolute value function. You can graph this absolute value function, but we also know that my absolute value function is a piecewise function. I have this negative 2x where x is less than 0 and a positive 2x where x is greater than or equal to 0. It makes that V shape. So that's what this side and this side, that's what makes that V shape. This is just a line here, right? This is a line because I know my vertex here is 0, 0, because there's nothing else back here, right? So my vertex is 0, 0. That tells me I have a line with a slope of -2, but it only goes to 0. And that's where it stops. It's a piecewise function, right? And then I've got my line with a slope of +2, but it stops because it's greater than or equal to 0. So I technically have this whole line and this whole line, but I only need these pieces of it because it's the absolute value part. Right. Okay? Okay. So here is a situation where if I have this vertex and we want to graph these and make this nice, I've got this as absolute value function, super easy graph we're looking at. This one is in standard form. So in order for us to graph this, we know that we have to get this in, oh, what color do we want to make it? Do we want to go blue on this one? We'll make our parabola blue. We have to find our vertex. And the vertex, anything in standard form, remember, x is equal to -b over 2a. Really pulling on that algebra. So now I have -3 over 2 times -1. So this is a positive 3/2. Oh, nice. All right. So because of that, interesting, then I plug in 3/2 to my function to get the output y value. So I've got a -3/2 squared plus 3 times 3/2 plus 6. Okay. So a -9/4 plus 9/2 plus 6. Are you guys with me? Looks like we're going to just need to go ahead with a common denominator, so let's just do that. So -9/4. Here, if I multiply this by a 2 over 2, and this is going to be multiplied by a 2 over, lies. 4 is my common. Okay. So this is plus 18/4 plus 24/4. So -9 plus 18 is 9. 9 plus 24, it's going to be how much? 33. And I'm graphing this on a graph. So let's make this into a mixed number. So 33 divided by 4 goes in 8 times with 1 left over. So my vertex here is going to be 1 1/2 and 8 1/4. Okay, so can we do the x, y, new y chart and come up with that? Absolutely we can. That's difficult to see. I'm going to rewrite it. However, I don't want to do that, right? I'm not trying to go in here and make something happen with that. So because of that, because when you do your x, y, new y chart, you're using full units. So if I'm starting here at the quarter and at the half already, yes, we can do that, but that just makes it unpleasant. So we are going to actually set these equal to each other and then try to come up with where they intersect, and that should be easier in order to graph. Okay, so I am going to actually go ahead with our graph down here and see what we've got going for us. I know my absolute value is going to go from 0 up, so I don't have a whole lot that I'm going to go down below. 4, 5, 6, 1, 2, 3, 4, 5, 6 that we have. The other thing that I already know is that 1, 2, 3, 4, 5, 6, 7, 8. Oh, we got to go up a little bit more because it's 8 1/4. So we don't really need that. I know my vertex is at 1 1/2, 8 1/4. So 1 1/2. So gauge it right here, 1 1/2, and up here at 1, 2, 3, 4, 5, 6, 7, 8 1/4. So 1 1/2 and 8 1/4, right about there. And I know it's going to go down because I have a negative as my A value, but anytime it's in standard form, remember you also have this coordinate point here of 0, 6. So I also know it hits up here at 6. 1, 2, 3, 4, 5, 6. So just use what you already know and pull that off, right? Okay, here's the other thing that I know. When I graph this absolute value function, we're going to go red on it. I know I'm starting here at 0, 0. Each one of these sides is aligned with that slope. So my slope is 2. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. On the other side, it's the same thing. Up 2, back 1, because that's my negative slope. And there is my absolute value function. Oops, let's try that side again. Make it a little bit better. Okay, now let's set these equal to each other. Let's try setting these equal. So I'm going to make this bigger so we can see it better. I have this negative x squared plus 3x plus 6 is going to equal this negative 2x because I want to see where is my function hitting where my slope here is negative 2 on that side, right? So let's do this thing. I want to have always, always, always a positive lead coefficient. So I'm going to add x squared, subtract 3x, and subtract 6, all right? But I want to write them on the left side. So x squared, if I subtract 3x, I'm going to get a negative 5x minus 6 equals 0. Do you see what just happened? I mean, you're in Calc 1, so I'm guessing we've got this. Adding x squared, and it doesn't matter. Whatever's on one side is equal to the other. So plus x squared minus 3x, and negative 2x is a negative 5. And then negative 6. I just like to have it on this side. Makes me feel better. So then you factor. So x minus 6, x plus 1. So x is equal to 6 and x is equal to a negative 1. Now look what's happening. I am saying, where does my parabola hit my negative slope? Is it going to hit it over here at 6? No. I'm on this side of my graph, right? So where is my parabola going to hit that negative slope? It's not going to hit it there. It's going to hit it right here at this negative 1. So they are going to have the same value at negative 1. Do you see that? Okay, because this is saying if I were to have this full line, this full negative 2x line, because you don't put, when you set these equal to each other, you don't put the parameters you do like you put it up here, right? So you just say, where are they intersecting? If this parabola had gone all the way through here, then it would intersect again, that I'm looking at this line going all the way down here. If it were going all the way down, it would intersect again at 6. It would intersect down there and up here. Okay, that's why that has two different values, because we've made it a piecewise. We're only looking at this part. Okay, now let's look at the other side. I have negative x squared plus 3x plus 6 is going to equal a positive 2x. I'm going to make this bigger again so it's not quite so small for you. And do that same kind of thing. I'm going to add my x squared, subtract the 3x, but I'm subtracting 3x from this positive 2, making that just a negative x minus 6 equals 0 because I'm subtracting that 6 over to this side too. You always, always, always want to have that positive lead coefficient. Just makes your life easier. And then you factor x minus 3x plus 2 because you need that negative 1. So x is equal to 3 and x is equal to a negative 2. Now look at what's happening over here on this side. This graph, I'm saying this whole 2x. Of these two options, x is equal to 3 and x is equal to negative 2, when you look at the x values that make this possible, over here for the negative 2, x can only be less than 0. That's why this is the only one. It's obvious with my graph. Because I have these parameters, x has to be greater than 0, so what are my options here? Right? So this is not going to work. I only have the 3. So at 3 over here, 1, 2, 3, where this hits at 3, that's where those two intersect. Right? That's part of having that piecewise function. You look back and say, what are my parameters? How is this going to work? And then you get those values. And I'm going to color again. Because this is the region that we're actually looking at. Did we get all that? That is the region we're actually looking at. So my region is going from negative 1 to 3. Now here's the deal. This is a piecewise function. Whenever I break up these pieces, how am I going to be doing some absolute value here? You're not, right? You're not. I'm looking at this in terms of pieces. It's obviously my parabola is on the top, but I have to break up this piecewise function to have this left side and this right side. Well, what do we already know about integration? We can split this up here. And for my integration, I can split this right down here, and I can break this into two separate integrals. I'm going to make this bigger. I've got the integral over here on the left, and I've got the integral on the right. So this is integral 1, and this is integral 2. Do you see what's just happening there? My whole interval is going to be from negative 1 to 3, but when you break this up, integral number 1 is going to go from negative 1 to 0. Integral number 2 is going to go from 0 to 3. Because I'm just adding areas. An integral is the area under the curve. So we're still going to take our top. This is still the top. This is still the top, right? This absolute value here is still the bottom. The absolute value on this side is still the bottom. It's still going to be top minus bottom. I just have two integrals that we get to take the area of, and that's what we're doing. So you got it on your paper. I'm going to make this to where we can see this easier. Oops, sorry, I'm moving it around so much. So for integral 1, I'm going to go from negative 1 to 0 of my parabola, negative x squared plus 3x plus 6, minus my absolute value here, which is a negative 2x on that side, plus my integral from 0 to 3 of my top function, which is my parabola, minus that piece of the absolute value. See what just happened? This is integral 1, and this is integral 2. I'm just adding those two areas together. It's just area under the curve. We learned how to split those up. Now we're going to do it. Cool, right? Yeah, it's cool. All right, so let's get busy getting busy. I'm going to go to the next page because we are obviously out of room here, and we're going to do these. So I have integral 1. Did I make that blue? Yeah, integral 1 is blue, integral 2 is red, right? I'm just trying to stay consistent. So I have my integral here of negative 1 to 0 of a negative x squared plus 3x plus 6 minus that side is a negative 2x dx. This is integral 1. And then I'm going to add to that integral 2, which is going to go from 0 to 3 of my parabola minus that side of the absolute value. And that, oops, that's bad. That is integral 2. So when you do this, I'm going to do them independently, right? I'm not going to try to do all this all at once. So let's look at integral 1 first. Integral 1 is going from negative 1 to 0. And then I'm going to go ahead and distribute that negative sign right here. And then combine those like terms because I'm not about writing this 50 billion times. So we've got negative x squared plus 5x plus 6 dx. Now I just have a parabola. So integrate that. Here I'm going to add 1. I've got this negative 1/3 x cubed plus a 5/2 x squared plus 6x. And I'm taking that from a negative 1 to 0. Plug your 0 in. Do you see how if I plug a 0 into every single one of these, what are you going to get? 0. So I'm not writing all that back out. But you are subtracting the next term, which does have value. So make sure you don't lose that out when you try to shortcut this stuff. I've still got negative 1/3, negative 1 cubed, 5/2, negative 1 squared, 6 times negative 1. So let's do this thing. I've got the opposite here, and negative times a negative will be a positive 1/3. And then this will be a positive 5/2 because it's a negative 1 squared. And then minus 6. So we can get a common denominator. What's it going to be? 6. 6 plus 6 minus something over 6. So that's times 2. That's times 3. And that's times 6. I'm going to go ahead and change those signs so I don't get confused later. And we have negative 17 plus 36 would be how many? 19. We good with that? Okay. Okay. There's our first integral. Now let's look at integral number 2, because we're just going to add these together at the end. But let's figure this one out. Integral 2 here, whenever I combine those like terms, I've got a negative x squared. I'm going to make this bigger over here on this side so it's easier to work with. Oh, a negative is going to be a positive x plus 6 dx. Then we integrate that. So I now have a negative 1/3 x cubed plus a 1/2 x squared plus 6x. And I'm going from 0 to 3. So I've got a negative 1/3, 3 cubed, 1/2, 3 squared, 6 times 3. And again, if I plug a 0 in for all those terms, we will be subtracting 0. Now I got a 3 and a 3. So one of these 3's is going to take out one of those. If you can ever make your number smaller, for the love of Pete, do it. So 9 times negative 1 is a negative 9 plus 9/2 plus 18. So put those numbers together. And I've got 9 plus a 9/2. So getting that common denominator. So I've got 27/2 is what I pull off for integral number 2, right? So integral number 1 is 19/6. Integral number 2 is 27/2. So if I add those together, 1 plus 2, I'll get 19/6 plus 27/2. If we get a common denominator, 19/6 plus, if I make that a 6, I need to take 27 times 3. What is that? 81. So my full integration here is going to end up with 100 over 6. And then reduce that, and I've got 50/3. There it is. All right, let me squeeze this in. So you have to know how to use the fundamental theorem of calculus. This is something that is common, that is easy to do, that I expect you to be able to do. Now, sometimes these problems take a little bit of effort, but you can do that. There's nothing wrong with that. All right? So just pulling that off. You can do this. You can do this. All right? I'm going to say one more thing real quick here while we're still on this problem is you can have different problems, all right, that are bounded. Like here we had to split this up. You can also have something that's like, here if I have this problem, but I have, this one going here, this one going here, something like that. And I'm told that I am bounded by the first quadrant. That's something that you can also have. So yes, I've got these two intervals, but whenever I am bounded by the first quadrant, I only have this piece of it that I'm looking at. Do you see that? So I'm not necessarily saying where do these two intersect everywhere, then I'm bounded by that first quadrant, which means let me go purple. Whenever I'm breaking this up, I have to break, oops, I got off on it. I have to break it where this intersects right here. You see what's going on? This is going to be integral 1, and this is going to be integral 2. I still have top minus the bottom, but my bottom in this instance right here is going to be y equals 0. And I still have the top minus the bottom, but the bottom of integral number 2 is going to be that actual function. Right? Okay, so if it's bounded by the first quadrant, don't get wigged out by that. You can still split that up like we did on that very last example, and then you can work with it. Okay.